never.
Yeah.
Anyway, really, the lecture starts now. The new lecture. No. Oh, sorry.
But from where did the gauge motivation came? Can you please explain a bit? Why did I want it to be a gauge theory?
Well, remember what I said? I think I started the course when we were chatting the first day. That if I want to have a gauge principle, I'm forced to have a messenger.
Yes.
This is something very profound. So just the very fact that there is a messenger already tells me that probably there is a gauge symmetry. Because it's the gauge symmetry that necessitates its existence. Okay, if I change the phase here, I said, and somewhere further away, okay, Elalis, then someone should communicate between the two of us in order that we have the same theory and the answer. The thing is that QED does possess this gauge symmetry. We know it from the times of Maxwell, okay? How it really works, the gauge symmetry, that you will learn in the next few weeks, I hope, 3-4 weeks with SAFE. That you must take my word for. The profound thing is, if you wish, okay, why not, since you asked? Okay, a few more words. You've written the propagator for the photon by adding a gauge term. You added a gauge term because you couldn't really find the propagator without gauge fixing. Okay, you can't invert the quadratic form. Then you found out that the propagator of the photon Q squared, doesn't matter, G mu nu plus a function of gauge Q mu Q nu over Q squared. I'm not even writing what it is, it's irrelevant at this point because Q mu Q nu do not contribute. Okay, they are gauge dependent. The reason they're gauge dependent because the photon couples, and now I can write it as well, to the conserved current. J mu, which is phi bar gamma mu, Q electromagnetic psi, is conserved. Which means that K mu J mu is equal to 0. So when you exchange the propagator, the pieces that go as K mu are gonna give a 0, acting on the current, right? What the propagator does. After all, what is this, what we are studying? Exchange of a propagator between these two currents. The process looks like J mu, D mu, or delta mu, or sometimes, right? J mu. And this fortunately goes away. So maybe I can answer your question a little better than just by hand waving. So what is crucial here, that this propagator goes as 1 over Q squared when Q goes to infinity. It has to do with the masslessness. I'm assuming that photon is massless, which is to say I'm assuming that there is a gauge invariance.
Yes.
But when we wrote the W propagator, let's write it again, more carefully, a massive gauge field, which I call W. I'll get minus I, Q squared minus MW squared. Notice this piece behaves equally. G mu nu minus Q mu, Q nu over MW squared, once again. Now what happens now? When Q goes to infinity, now why is it so important that this goes 1 over Q squared? Because we are doing integration, let's say D for Q, over the terms which involve the propagators. But you're integrating all the way to infinity. If something is, the integral is supposed to be finite, the integrand must vanish at infinity. And the integrand are the propagators, so they better vanish at infinity. Okay, this is crucial. This goes to 0. And it goes pretty fast to 0. It's not logarithmic. It's better than that.
So if you integrate it over D4?
Right.
They still diverge?
Well, they don't. I'm not saying that it is sufficient. I said it is necessary.
Oh, okay.
Integrals must be vanished. By the fact that integral vanishes doesn't mean that the integral is finite. Okay. Well, this must vanish. Okay, integral actually then it will be finite. But you may say it depends how many propagators I have. Yeah, of course. But that's why we looked at the physical process in which this was finite. But okay. So let me put it the other way. If the propagator does not vanish, and look at this piece, this vanishes when I go to infinity, but this does not. This goes as q squared over q squared. This goes as 1 over mw squared. And now it's a dilemma. Should I wait for another question, or should I say a little more? When you read Feynman lectures, he said he had a great teacher when he was in high school because the guy knew when to stop. And that's why I'm a good physicist, he says. Then he says, I don't know when to stop, that's my problem. But I think Feynman knows when to stop. I don't know when to stop sometimes. I want to go on and tell you more, but it would be better if you had a problem. Because you can tell me. But let me ask the question you should ask me. If this is such a thing, looks incurable, then why am I pursuing it? And since I don't know when to stop, let me give you a hint. Let me bet you once. This is okay because of gauge invariance. Gauge invariance guarantees that there is no such term. Okay? Observed current, massless photon, all of that. But how did I get gauge invariance? I got it because I had too many degrees of freedom. If I had worked with physical degrees of freedom, there would be no freedom whatsoever, no invariance. So in the case of QED, I wanted to work with a mu in order to have a compact Lorentz notation which guarantees me Lorentz covariance and eventually invariance of the theory. So I've worked with 4 degrees of freedom, but the physical degrees of freedom are the transfers, right? Let's call them A transfers. Degrees of freedom perpendicular to the vector of motion, okay, to the momentum. So there are 2 physical degrees of freedom. So you see, I have 2 extra degrees of freedom. This is when MA is 0 in a gauge 0. This is my massive guy. Let me keep it here. Now here I also work with W mu, which has 4 degrees of freedom. How many physical degrees of freedom? 3. It's a spin 1 particle. So minus, okay, physical. That's 1, which is 3, is 1. So what was 2 before now is 1. See, this was such a serious problem in the 60s that this propagator drove them crazy. Weinberg, a father, one of the fathers, you know, with Gleshow, the standard model, spent years trying to make sure that the theory works, but he kept using this propagator. It's very interesting because it's in the 50s, the solution was actually found but completely ignored by a fellow called Stuckelberg. Stuckelberg, a Swiss physicist who's independently developed the Feynman rules. He was developing path integral and actually solved this problem, and his work was completely ignored. He was told to have mental problems, he would end up in mental houses. It's an incredible story. Today we are more and more emerging that he was a genius. So what he said, we'll come back to it, but I want to bet your mouse. He said, why don't I imitate what happened here? If I have 2 extra degrees of freedom, maybe I can recover gauge invariance. Remember how this propagator came about? We wrote the mass theorem. This is a digression, a 5-minute digression. You can relax completely. This we will study carefully. I just want to give you a feel. He said, instead of writing this, why don't you do the following? Add a degree of freedom. It's stupid. Why are you adding degrees of freedom in a sense? You already have 1 extra degrees of freedom, okay? But because it were here, we have 2 extra degrees of freedom and we had gauge invariance. Notice he says you will get gauge invariance immediately. Obviously. If A mu goes into A mu plus 1 over G, let's say coupling constant, D mu theta or alpha, then as long as G goes into what? M over G theta, am I right? Sorry,
No.
plus G. I get gauge invariance. If people have paid attention to this, it's a pity there was a lecture by Weinberg in the fall. You guys were here already?
Yes.
It was a beautiful lecture. I had a back problem. I've injured my back last time, so I had to walk out. Because I just couldn't stand there or sit down. And I wanted to ask him when I was coming back. I've always wanted to ask him, actually. I was corresponding with him. I would write to him. Something that right. Why did they ignore this work? They didn't know about it, or they didn't take it seriously? Had this been taken seriously, then the history and the way of teaching would be very different. Everything would have been already there. There would be no introduction whatsoever. Okay, you would have worked like this. Why? You're going to do the homework. Once you recover the gauge symmetry, we will recover a good propagator. We'll put a gauge fixing term and so on and so forth. I leave it for the future. Fortunately, I came late and I asked the question. Well, the history of the standard model is basically all of them being ignored. It takes years before another paper would appear. So, now that I've read your mouse, you can take my word, I'm going to cure the problem eventually. What the Stickelberg did, Hooft rediscovered in a more systematic manner. So let's take it seriously, the possibility that W also belongs to the gauge symmetric messenger line. So what did it take us? To the SU2 gauge symmetry. It couldn't be U1 because there is a charge. W carries charge, and U1 messengers do not carry charge. And what this means, the d mu is d mu minus IG TA. This is what I mean by SU2 today. That's all you have to know today. And then we said the simplest possibility that we are going to pursue, that there is a doublet of states with upper and lower component, which is equivalent to say that TA is sigma A over 2. And we found out from the covariant derivative that the interaction Lagrangian, which is G psi bar gamma mu TA A mu A phi, please check your notes, is equal to G over square root of 2 U bar gamma mu D W mu plus Hermitian conjugate plus G phi bar gamma mu D3 phi A mu 3. Where I introduce new fields W mu plus and minus as a linear combination of 1 and 2. I normalize them, therefore I get G over square root of 2. This was actually attempted by Glescher in 1957. As soon as the form of the weak interaction was established, Schoenberg tried to construct an SU2 gauge invariant theory. Well, he was hoping, the idea was that you will get electroweak interactions. There were 3 messengers at that time. W plus, well, there was 1 messenger and 2 imagined, there were weak interactions. W plus, W minus, and Z, and photon. So the hope was, this works beautifully, you agree? This is the way the W boson does interact. Up to the helicity structure, but at least the form of the interaction is correct. And this we decided, unfortunately, failed. Because in this case, in other words, what would you predict here? That A mu 3, if you ask if this is a photon, if you ask this question, you would predict that Q is T3 and that E is equal to G. It's a beautiful theory because it first unifies these weak and electromagnetic interactions. The coupling constant is the same. And quantized charge. Quantized charge. This is beautiful, but wrong. Now the rest, if you follow it, we can do together with little input. We can actually, you can participate in the construction. Once you get an idea, you will see most of the developments of the standard model required brilliant ideas, simple ideas, but technically, until the time of 't Hooft, it was not so hard, the construction itself. So what should we do? Notice this is 1957. It will take 4 years that another attempt is made. Okay, Glescher in 1961. It's kind of appropriate. He was a student of Schwinger, that he would come up with a theory. So instead of giving up, he just took courage and said, well, let's just, okay, the minimal theory didn't work, so make it a bit less minimal, okay? Make a compromise. Obviously, I have to enlarge it, you agree? It just didn't work. In other words, this can be a new gauge boson, but it cannot be the photon. So I must have SU2 cross U1 as minimum in terms of the counting of generators or messengers. And so I asked you a question last time, can this be electromagnetic? No, because the direct product is equivalent to say that Q electromagnetic would then commute with SU2, but that we know is not true. If Q were to commute with SU2, this guy would have the same charge, but they don't. So we decided this could not be electromagnetic. This new charge is called hypercharge. So that hypercharge does commute with TA. That simplifies this. Your memorizing at least, or figuring out these funny new charges. I don't want you to know them. I do want you, I appeal to you to know the particle charges, up, down, quark, and electron. That's all you need to know. Okay, because the families repeat themselves. But this we can derive. Now actually, the original theory that we attempted had another problem. QED conserves parity. Weak interactions violate parity. The actual form of weak interaction Lagrangian established by Marshak and Sudarshan would actually look like this. In terms of the messenger doublet, it is coupled only to left-handed fragments. This is a convention, please remember, right? What I call first, what I call left. The fact that it's coupled only to left. This is just a convention. There are a few other conventions, okay, that will emerge. The first one, all is left. And that told me that I had to do something outside of SU2 because I can't have at the same time parity breaking and parity conserving. So to emphasize that the weak interactions are purely left-handed, we put L here. And this means that the original doublet must be left-handed. Let's now take seriously the particles that are involved. These are actually up and down. We now use for up and down quark. So according to the weak interactions, according to Marshak and Sudarshan, the right-handed quarks must be singlets. They cannot fill doubly. Okay. Same way for neutrino and electron, which I said, and it's a confusing notation. Sometimes by up and down, I mean up and down quark. Sometimes mean upper and lower component of the doublet. Okay. Which for leptons is UL. These are we call QL doublet, these are we call LL. ER must be a singlet, and UR, if it exists, must be singlet. We never saw it. The fathers of the standard model wanted to construct the minimal theory, so they postulated a theory of only visible, already existing particles. Right-handed neutrino was assumed not to exist. This is what we call matter. This is what the universe is made of. Now we may say, okay, please be careful with the notation. It's surely not made out of neutrinos, universe. Right? There are no neutrinos here. It's made out of atoms, which is made out of nucleus and electrons going around. Well, I don't know how much cosmology you know, but you are learning it slowly. You know that the universe was hot. Well, you've been reading popular articles if you were not doing cosmology. It was very hot in the past. We know that the temperature of the universe was surely above MeV in my funny units, which is about, this is very hot. This is about 1 eV is about 10 to the 4 Kelvin. So it's about 10 to the 10 Kelvin. Let's say it was bigger. At these very high temperatures, you know what happens at high temperatures, okay? Okay, digression again. I do the things in order for you to see connections in physics. What happens at high temperatures? You know, when you have time, you create equilibrium. The particles interact like crazy with each other. And typically what happens if there is enough time, and it turns out that there is enough time, you will learn that. It has to do with how fast the universe expands. You create equilibrium. In other words, the particles of the standard model will be equilibrated even if they were not initially. Therefore, the number of each species is more or less equal to a number of other species. Like neutrinos were there. And they got frozen because they have weak interactions. So according to the Big Bang standard model, cosmological standard model, there must be a sea of neutrinos around us. Just like the sea of photons that was discovered accidentally in 1967 by these two guys that wanted to calibrate their antenna, you know the story. So they had to calibrate it and they found out most amazing thing, that the universe is filled with radiation. There should be a sea of neutrinos. Why don't we see it? What do you think?
Yeah, too weak.
It's very hard to see. A cross-section depends on the strength of interaction and depends on your kinetic energy, okay? And you will learn, if you don't know already, that the temperature of the universe,
2.7.
yeah, it's very small, right?
And the answer is even low.
T0, let's call it, okay? That's a very small kinetic energy. It's very, and you know, when you have a sea of particles, the average kinetic energy of a particle is more or less given by temperature, okay? K is equal 1, Boltzmann constant. Anyway, so this is the reason I call this matter, actually. Universe is supposed to be made of this. Short-sighted mark forward. So now, what it means, these are doublets, right? Let me call these doublets in my notation, and these will be singlets. So what I mean that TA acting on a doublet is sigma A over 2 acting on a doublet, whereas TA acting on a singlet is?
Just identity, 1?
No,
Oh,
0. The transformation is 1.
Is that joint?
But remember that U is e to the I,
yes.
theta A TA. So true.
When you're talking that the joint action between the singlet and the TA?
No, I'm just defining the quantum. I'm just defining what I mean by singlet.
Yeah.
This is what a singlet is by definition. It's a particle that fills no SU2. Okay? As Vasif wanted, this is equivalent to saying, this is equivalent to saying that U acting on a singlet is equal singlet. It doesn't transform, it doesn't feel it. It's a singlet. It's invariant under the SU2 operation. Okay, that's what I need. So what I mean by SU2 cross 1 theory, that the covariant derivative is going to look like this, minus IG, dA, A mu A. This is the SU2 part. Agree? SU2 has a coupling constant G. U1, let's call it G prime. So I will have minus I, G prime. The charge I'm going to call Y over 2. Y over 2. Because everybody else calls it Y over 2. There is a historical reason, it doesn't matter. It's irrelevant what I call this charge. All of this here I could always renormalize. Well, it's just a name.
Yeah.
But even if I fix the name, I can renormalize G prime, I can change it. Okay, all I have is the product of this. And the U1 generator, the new U1 gate boson, predicted by this assumption, I call B. Now, I don't know what this Y is, and why I don't know, because I don't want to learn it. It's some new quantum numbers. What I know is that the electromagnetic charge must be a linear combination of T3 and Y over 2. How do I know that? Well, this is diagonal, so it must be the sum of the diagonal generators of my regional group, okay. This looks a little clumsy, but remember when you write the electromagnetic interaction, what you have E, Q electromagnetic. This is not predicted by anything, this is a number that you measure. You can always call this E prime. So let me write like this. Well, let me not do it. T3. You see, T3 is fixed by commutation relations. T3 I cannot change. As you know. the SU2 commutation relations which we wrote the other day, which you know in your sleep, epsilon ABC, fix the normalization charge is quantized. So I can, but I can renormalize this, you agree? I can say that this is equal to QEM prime, that this is equal to A QEM. And then E prime would be E over A. It's the product that I can measure all this. So I have that QEM is T3 plus B Y prime over 2. Well, Y prime is completely arbitrary because it multiplies an arbitrary coupling which I don't know. So I can redefine that. In other words, I can say that B Y prime is Y. So Q electromagnetic is T3 plus Y over 2. This is the most general form I can write. I'm not cheating here. So that means, how should you read it? You should read this, that Y over 2 is Q minus T3. That's for us a derived quantity. You and I will now, from now on, remember Q and T3. Okay, we'll make a little effort. It's very easy to remember T3. If it's a doublet, it's a half minus half. If it's a singlet, it's 0. And charges, presumably, you remember. Therefore, if I ask you, what is the hypercharge of, say, these doublets? What is the hypercharge? I need the hypercharge of QL, charge of LL, and then the hypercharge of right-handed particles. Notice for the right-handed guy, it's simple because there is no T3. So from here, immediately, any hypercharge of any right-handed state, fermion I'm writing here, is twice the charge. So tell me, what's the hypercharge of UR? 4/3. Well, let's write like this. Minus 2/3 and ER minus 2. What about the doublets? Well, we can take members of a doublet, but what we should remember that they must have the same hypercharge. It helps you. So look what you can do for a doublet. This is a little simple trick. Y over 2 plus Y over 2, if I sum the left and right hand side on a doublet acting. So in other words, on a doublet will be equal Q up plus Q down, you agree? Mm-hmm. Plus T3 up plus T3 down. But that's traceless.
That's 0.
So for any doublet, it's simply the sum of the up and down charge. So you can be fairly quick. If I ask you what is the hypercharge of a leptonic doublet, well, the sum is trivial. Minus 1 plus 0 is minus 1. And the quark doublet?
1.
1? Yes, but it's well, 1 is there. But, okay.
No, it's 2 by 3 minus 1 by 3.
Right.
So it's minus 1 by just 1 by 3.
You don't have to remember that.
Alright.
You can always derive it by going back to the formula. You can check the formula by looking first at the up quark, say, and then look at the down quark, and please make sure that you get the same number. Okay. If you have trouble with this argument, okay, just do it brute force. Here is the formula. Take the particle, read it of its charge, and read of T3, and you will get the average charge. But since I know that they must be equal, I get this. By the fact that I took only left-handed doublets, I reproduce weak interactions trivially. You agree, the W boson. That we checked already last time. How we got it? Because sigma 1, sigma 2 being off diagonal gave me immediately this charge changing interaction. Okay. So from this covariant derivative, I think we need a new blackboard here. Fernando was very good actually as to sort of understanding things when we talk about bar and other things. I can see how it gets deteriorating as we go on. Now they don't want you to illuminate it, okay? Because apparently. So once again from covariant derivative, for what I get, I start with psi bar, I gamma mu d mu psi, and that reproduces the interaction psi bar, gamma mu, g dA, a mu a, let's write it all the way, that's g prime, b mu, and I can write q minus t3 phi. Y over 2 I got rid of, okay, because these are my fundamental quantities, okay. So what we said here, TA, T12 being sigma 12 over 2, gave me immediately the off-diagonal piece, and that produces G over square root of 2. Any up gamma mu dl, W mu plus. So in other words, let's be more complete and write it down. There will be nu L gamma mu EL. Just for the sake of completeness. This happens with any doublet. Okay. You see, the beauty of SU2 of non-abelian gauge theory is that once you specify a representation, okay, this is true of any gauge group. If I said that I liked, say, SU5, I could immediately make statements, okay, because everybody inside the gauge group behaves the same manner. And this is what made it beautiful. When I took SU2, I predicted the charges. I actually predicted it. Here I can't do that because this bloody Y is arbitrary. So this is what we have here, the charged. We call them charged weak interactions. Charged interactions mean that the messenger carries charge. So let's do the neutral one. Let's see if I can do it in a... This is the reason that you and I are going to pursue this, okay? So of course you can tell me it's trivial, right? I'm bugging you with this. The reason we are pursuing that this theory has been checked to 1 in per mil, right? It's a now high precision theory, the electroweak standard model, okay? But I want to tell you why we all got excited at that time. The beautiful prediction that emerges immediately in the neutral case. So in the neutral part of the Lagrangian, I have psi bar, gamma mu, See, the beauty of the neutral thing, I don't have to write up and down because the generators are diagonal, okay? So I can have a concise generic notation. So I have T3, A mu 3, G, you agree, plus G prime, let's write it, B mu, Q minus T3. Fine. This is my neutral, okay? So I could, why take more space? Now, you and I decided that this could not be a physical particle. B could not be the photon. A3 could not be the photon, or whatever else is happening there, because if this guy were the photon, then this would be the charge, it would have to commute, and so on. Therefore, I can write, and let me write here. That means that these fields are linear combinations of physical fields, okay? Which I will write, let me write sine, just as S, well, let me write like this, S, A. I'm anticipating that there will be a photon, plus C. I'm predicting a new particle, obviously, right? I have 4 generators, this is not surprising. B mu then will be C A mu, must be orthogonal, minus S, Z mu. This is the most general way I can write, because I want to preserve the normalization. The same way that the W get the square root of 2, this must be sine and cosine, okay? S is sine theta, and C is cosine theta. So that means that I get psi bar, gamma mu. Okay, GT3, let's just write down. S A plus CZ mu plus G prime. What is B? C A minus SZ mu Q minus T3. Fine. Okay, this is Glescher 1961. Notice that there is no mention of some Higgs particle or whatever. Okay, I'm just constructing the structure. So let's isolate them. What do I get? I get psi bar, gamma mu. Let's take A mu out. What do I get? I have T3. T3 has G S minus G prime C. Why am I saying? Yes. Minus, right?
Yeah.
C comes with minus side. T3 I'm looking. Plus Q. Q has coefficient G prime times C. This is A mu. Plus Z mu. Bear with me because look, I'm not looking at the notes, so I can make a mistake, so help me. I'll T3, what do I get for T3? I get GC, am I right?
Mm-hmm.
Plus G prime S. T3. And then Q will come with a negative sign. Minus G prime S Q. I think we got it.
Yes.
That was gamma mu psi. Here it is. We are almost there. Now comes the crux. Glescher cannot predict that there is a photon. He doesn't know. Notice what he's doing. And you may try to say, you know, maybe this is 1962 and you were young and you are saying, well, I know this looks a little stupid, you know, there were Pauli students were talking about, but you wouldn't say that because Glashow was young. People don't speak of young people like that, usually people when they come to their age. But he was not completely stupid, and yet somehow he's doing something stupid, it seems. After all, he's writing a symmetric theory. But the world cannot be this symmetric because photon is massless, W is not massless, okay? He's sort of being a bit schizophrenic, he can't decide, but what he means, he says, look, whatever defines basically the interactions of particles, it's written in the interaction Lagrangian. That is unchanged with energies. Or maybe the coupling changes, but the form doesn't. Okay? When you scatter electron-electron, at any energy it behaves the same way. The coupling constant changes with energy, it's called running. But the form of the effective theory does not. Okay, this is very important. So, well, the masses, he says, I know that the masses are different and that there is no symmetry. But when I go to high energies, the masses become irrelevant. So I'm hoping that the fact that I am doing something illegal will be cured by some deeper principle. My intuition tells me that this will be cured because when I go to high energies, masses will be irrelevant, okay? And we know actually today it's true, okay, because we have a way of doing that. It's called the Higgs mechanism. We came after him. But this intuition turned out to be very important. So he says, I will assume that there is a photon because I see the photon, okay? The same way Einstein says, I have to agree with Newton at high energies, okay? There's any beginning of a new theory, you make sure that you agree with the existing phenomena, which means that this must be zero. Photon does not couple to P3. If it did, then a neutrino would carry charge. So I predicted something which is called weak mixing angle, tangent theta w. In other words, theta is theta w here, so the tangent theta w is g prime over g. Right? G prime c is equal to gs, or if you wish, sine theta w is g prime over square root of g squared plus g prime squared. And cosine theta w is g over square root of g squared plus g prime squared. This arbitrary mixing angle became something very profound. The particle mix precisely the way the coupling constants mix. Okay. This is not trivial. Then I will get a correct interaction if I say that G prime cosine, so let me write C from now on is equal to E. But that's equal to G as W, we agree, from the relations that I wrote here, or from the fact that they cancel. So notice the first thing that the gauge theory would teach you, the weak interactions are not weak. Actually, they are stronger than electromagnetic, slightly stronger, because this is always less than 1. It turns out that this angle is not that small, but it's about 30 degrees, as we'll be learning. So E is smaller than G, ironically. The reason we thought the weak interactions were weak is just that this heavy fat messenger was too slow. But if you give it enough energy, okay, then you get more or less the same interaction. Okay. That's the beauty of this gauge picture. And now it's now a matter of just a little algebra to write down the Z interaction. So we predicted the existence of a new neutral gauge bosons. Okay, clashes. There is Z mu. And its interaction is uniquely predicted, okay? If photon exists, Z has a unique form. And it's written here. And you can see immediately I get GC will give me cosine square, G prime S will give me sine square. And I'll get G over cosine theta. I will take cosine theta W out. Let me write the full form here. Psi bar, gamma mu, okay, Z mu coupled to this. T3. Okay, are you with me? You see that? I had GC with G prime S, I think, right? Is that what I had? And that I can write as what is a smart way to write it? That I claim I get that, I see that. Let me write as little writing as possible. Okay, G is, okay, I will write it as 1 over CW, G, then I get CW squared from the first term. From the second term, I have SW, but here I have another. There is tangent at a W. Notice the tangent at a W is G prime over G, so I get SW squared. So we get that. And then what I have is G prime times S. This will make it, there is a tangent, but I took cosine theta W, so you get sine squared theta W times Q. It's a very similar interaction. Universal, just as the phone is. Right? We like the QED interaction because it's enough to know a quantum number of a particle, okay, and then the form is fixed by the gauge structure. Once again, we see that. Then I need two quantum numbers. It's a little more complicated. Apparently in the 60s, I have to remember which experiment, I'll try to dig it out. There was an experiment looking for such interactions, okay, and there was a graduate student who saw it. That what looked like a new neutron interaction. And he was hushed up. I think it was he. The theory was not yet written. Once again, you know, the history of the Standard Model is a history of great achievements, but also missed opportunities, okay? The irony of fate. If you had seen this weak interaction before, right, then you would have immediately accepted this. But it's interesting, when Glescher writes this paper Glescher's papers did exist, well, I take it back. No, this was a bit later. But it will be ignored for 6 years. In 1967 only, Weinberg will decide to follow up on this and write the modern version based on the Higgs mechanism. And Weinberg himself will be completely ignored. Not only that everybody else ignored Glescher, but Glescher also ignored Glescher. In 1961, he writes that. In 1964, Glescher writes a paper with Bjorken, another great physicist. He never got a Nobel Prize, strangely enough. He's one of the father of the modern theory of quarks. Bjorken scaling. This is a guy who taught experimentalists how to see the quarks. They didn't know what to do. This MIT slick experiment, but they got the prize. He didn't, strangely enough. So Bjorken, and they write this paper in which they add a charm quark to this structure, but they don't cite Glescher. Glescher somehow, I guess I always wonder what happens, okay, to you, but it's not easy to take yourself seriously if nobody else does. It seems. You're always sort of taught that great, beautiful ideas are recognized immediately, okay? Not true. I wonder what is going on today, Rich. I'm not recognized, for example. I'm always intrigued. I'd like to know whether I would get recognized. You know, there are painters you love. I love Van Gogh. But it's very likely I wouldn't have bought a painting of Van Gogh as nobody else did. Okay. It's easy to recognize a genius afterwards. Okay. I think this should have been pursued. To me, it's obvious. Such a clean, precise prediction based on the structure itself tells you that you're on the right track. You very rarely get predictions which you cannot touch, that are not product of your playing with the phenomena itself. So what I need to do, okay, let's write down now what I mean by this interaction, effective interaction. I want you to do a little more, but it's always a bad idea to start a new thing towards the end. Okay, we postpone this for Monday, and let's just look at this a little more carefully. So we said we have first the W charge interaction. So let's look at neutron decay, down quark becoming an up quark. I use a modern language. Electron neutrino. And we said we'll have G over square root of 2 squared. Let's not worry about factors of I at the moment, okay? Just the overall structure of the amplitude. G over square root of 2. U bar L, the interactions are left-handed, gamma mu dl. G mu nu over mw square. At low energies, remember, the only thing that remains from the propagator is 1 over m square. Then I have here electron coming out, EL bar, gamma nu, nu L. Neutrino entering, anti-neutrino going out. So that's G square over 2. But there is a factor of 2 here. You will become immediately the factor of 2 here if I write it as gamma mu, 1 plus gamma 5, E. E bar, gamma mu, 1 plus gamma 5, nu, mw square I. 2 came from the definition of left, which must have a half. 2 from the definition left. So I get that G Fermi, which we often call with the square root of 2, is G square over 8 mw square. Well, I like E rather than G. E was measured. That was a quantity that emerged from the, by the time measured very well. So I get 8 mw sine theta w square. So see the beauty of the standard model, there is basically just one parameter. If you tell me what theta w is, it's true, I can't predict it, but if you tell me what it is, I can give you everything afterwards. I get immediately the form of the the form is already there, sorry, and the value of the W mass. This I know, GF was measured, right? And we know today that, I don't know how you remember it. You should remember theta W is around 30 degrees. Sine theta W is about a half. If you wish more precisely, sine squared theta W, maybe you have seen it, is, someone knows? 0.23, even 1. Even the third decimal point is 1, okay. This series has become, after left, a high precision 1, okay. Not like UED, but getting there. Slowly, but surely. And that corresponds to MW of 80 GeV. This is very close to a quarter, which gives me 30 degrees. So I kind of like to remember it. Very often when I'm lazy and I want to get quickly a number, I put a quarter here because it's much easier than if I don't want to use a computer or calculator. So notice that once I know theta W, I also know the properties of the Z current. Okay, it's fixed uniquely.